Thank you, Jasmine. This is the work of my PhD student, João Neto, and he has been working on various devices which then lead to building blocks, which then lead to possibly at some point in a neuromorphic electronic skin. So here is the motivation. If you look at our skin, it has distributed receptors, distributed actuators, and distributed energy, distributed computing, etc., and all embedded in soft materials and flexible substrates. So, in a sense, if you look from the artificial skin point of view, you can see sort of a layered structure, having sensors on the top layer, but then electronics also near to the sensor, allowing you to have distributed sensing as well as distributed computing. If we don't do that, then we will be collecting a lot of data, and you need to transmit that data to certain location where you can process it. Now, communication in that process becomes quite challenging, and our body has found its own ways to deal with those challenges. And one of the ways is to start processing the point of contact itself. And that's where you are looking at distributed computing near to the sensor. So the device that I will present in this talk is something that you could see will be placed close to the sensor itself and would allow some level of processing at the point of contact, not complete processing, but is a partial processing. So, and there are several in the literature, you'll find some similar architecture other groups have reported, including my team also, where we got synaptic transistor. We have got a backgated transistor that was reported recently. Then there have been arrangements such as split gate as well as multi-gate devices. In this case, this was quite similar to what I'm presenting, and dual gate device such as this one from Siemens. With this background, here is the outline. Motivation I have already spoken. So the device that I'm going to present is based on silicon nanoribbon, and I will explain how we fabricate these devices using direct roll printing method, the method that we developed in my group. And using this method, then how we get multi-gate transistors. I will also present the fabrication of these, the electrical characterization of these devices, and then I'll conclude this talk. So in terms of fabrication, silicon nanoribbon, we start with we have tried both bulk wafer as well as soy wafer. But this example is the soy wafer. You have N-type silicon, then you have basically you using a photoresist, you define these structures which lead to nanoribbons eventually. The top layer here is 70 nanometer thick. So once you have these this photoresist, you define this window, you etch the oxide underneath, and after etching oxide underneath, also there's a selective doping also that takes place. Once you do that, this is the doping, this is the fabricated device, and you etch the oxide under the ribbons, and after etching, you get structures such as this one shown in the cell image. So you got now the doped area as well as ribbon, which are then transferred using direct roll printing. Now, with respect to in literature, there are lots of paper you will come across about transfer printing, which is an interesting technique. Many of work from John Rogers' group are based on transfer printing, in which you define the structure, you develop the structure as I explained, and then using a PDMS stamp, you pick these structures from the donor substrate and transfer them to the receiver substrate. So, and then after that, you process them further to develop the device. But problem with this approach is that it leads to many residues of PDMS on this surface, which are difficult to remove. PDMS being a dielectric material, and a thermal insulator, electrical insulator as well. So when you do metallization, then often you don't get a good metal contact. And that's an important part of any, if you are looking for high performance and stable response of the transistor. So in our case, what we have done, we don't use any PDMS. We developed this setup, which we call as direct roll printing. And in this case, you have the receiver substrate, donor substrate, which is the wafer. Using standard lithography method, you get your nanoribbons here, as I was showing in the previous slide. So these are the nanoribbons before they are transferred. And this roll has the receiver substrate. In this case, it's a polyimide with a partially cured polyimide also on the roll. And then you bring them in contact at an optimal pressure. When you applied optimal pressure, this roll will start rolling over the substrate and will pick up these ribbons. So in that regard, we don't have any PDMS, so it makes the process quite simple. And registration issues that were typically associated with the transfer printing, we don't have those issues. And residues, contamination issue also is taken care of. And of course, number of lesser fabrication steps means the overall process is much simpler and much faster. So this is the outcome of this step. One example is shown here. And this video, am I able to play this video? You should. Need to try.
Bit to the left, yes. Yeah, nearly.
Yeah, this video shows how the system works. So once they are in contact, this was a different sample, not the 2-inch wafer that I showed in previous slide. So at 1 millimeter per second speed, this goes, and about 10 Newton you are applying between when these are in contact. So when this roll process is over, we obtain a quite nice transfer. We have noted 95% yield using this process, which is significantly higher than the conventional transfer printing. And we got a registration less than 100 nanometer using this process. So yeah, these are the kind of different experiment or arrangement that you see. We tried this process on different substrate. This is an example of copper foil. This is PET, and this is aluminum and magnesium foil. You can see the transfer process is quite nice in all these cases, even though surface properties, they vary depending on the substrate. We also check the residues. This is the image that you see. We did not find any residue on the silicon ribbons in this case. And we tried different forces, as you see, 2 Newton, 8 Newton. And we noted that when you bring them in contact and apply the pressure between the donor and the receiver, that the overall transfer yield pretty much depends on this. So 2 Newton, it's 62, about 63%. And when you make it 8 Newton, it goes to about 87%. And at 12 Newton, we get about 95%. So there's still a room for improvement here. And that's our, a process that we continue to refine. Our goal is, of course, to take it as close to 100% as possible. And that's the basically yield that is plotted with respect to contact force. Now, using this process, what we did, we got the transistors. These are the doped regions. This is still on the wafer. You transfer them on the receiver substrate, and then you define source and drain line. After that, you deposit the floating gate. And then on top of floating gate, we then have two, there's of course the oxide in between, and then nitride here. And then you deposit two gates, gate G1 and G2. So that is something similar to this structure that you see here. You can have as many gates as you like. Well, of course, the device size would vary, or you can have this width of the gate can vary. The gate width would define the weight, basically, in this case. So depending on your prior training, what you want to have, you can embed this into the device itself. So this is the overall structure. You got the silicon, then silicon nanoribbon, then you got the floating gate here, then you got nitride, and then multiple gates. So that is quite similar to the different branches that you have at synaptic junction. There's a summation taking place. So in this sense, there is a summation that takes place. Typically, if you do the similar operation, you may need several number of transistors, large number of transistors to implement logic functions. In this case, the same device can be used. So in terms of electrical testing of each gate, this is the arrangement devising scheme shown here. That is the response from gate 1. There is the input output characteristic that you see here. There is a hysteresis, possibly because of the surface state, charge trapping, detrapping, etc. And this is gate 2 when you characterize this device by individual applying voltage, bias voltage at individual gates. Now, when you have applying bias at each gate simultaneously, you on both gates you apply the voltage. This is the response that we get for different VDS 1 volt and drain source voltage in this case is 5. And this is the gate source 2. It minus 10 to plus 10, and this is GS2 again. This is GS1, gate source 1. That's the kind of voltage we obtained from these devices. The important thing is here, which is how you would then interpret it. If you look at this response, this is gate voltage, this is VGS1, this is VGS2. So you are applying at one gate. This is the response of the device. You are applying at one gate, the first one. The 2, in this case, you get response from this. But when you are simultaneously, you get summation roughly, it's not roughly, but you get much higher than both individual gates, which we interpret as summation taking place within the device. Of course, there's a lot of improvement needed in this type of device, but that's the initial results. They indicate a good level of summation taking place. In this case, as you see here, this is the response to GS1, response to GS2, and when both are there, so you have much higher response on the positive side. So that way we are trying to connect it to develop a sort of logic with this type of arrangement. So that brings me to the end of my talk, and the conclusion and outlook is that this work presented the fabrication and direct roll printing approach for silicon nanoribbons based transistors on flexible substrate. Particularly, I showed the multi-gate silicon nanoribbon transistor fabricating, which was fabricated and characterized as you've shown in the results. Top gate showed electrostatic coupling with the nanoribbon channel. Initial results shows the threshold and on current modulation while using both top gates simultaneously. As a future step, we would like to demonstrate multi-gate nanoribbon transistor for reconfigurable neuromorphic systems, as well as something that allows sort of online learning. Thank you.